Billions of stars stretch across the canvas of the cosmos, each one silently posing a question that has echoed through the ages. Are we alone? This age-old inquiry gained a revolutionary ally with the launch of the James Webb Space Telescope, JWST. This marvel of engineering isn't just a telescope. It's a time machine, a magnifying glass, and a window into the early universe. Designed to observe the most distant galaxies and faintest objects, the JWST has dramatically altered our perspective on space, unlocking secrets hidden beyond the limits of previous instruments. One of the most sensational breakthroughs came when JWST turned its gaze toward an exoplanet known as K218b, located about 120 light-years away in the constellation Leo. Previously classified as a super-Earth, this distant world quickly stirred excitement among astronomers after JWST detected something extraordinary. Possible biosignatures, chemical fingerprints that could indicate life. Among the gases detected were methane and carbon dioxide, which, when found together in a certain balance, raise intriguing possibilities. But perhaps even more captivating was the potential presence of dimethyl sulfide, DMS, a gas on Earth known to be produced exclusively by living organisms, specifically marine plankton. If confirmed, this could be the first time humanity has sniffed out a sign of life beyond Earth. K218b orbits a cool dwarf star, and what makes it especially compelling is its location within the habitable zone, the region around a star where temperatures might allow for liquid water. But there's something even more intriguing. This planet is thought to be a Hycean world, a term coined to describe a planet with a rocky core and a thick hydrogen-rich atmosphere, possibly enveloping a global ocean. Such worlds could be far more numerous than Earth-like planets, suggesting we may have been looking in the wrong places in our search for extraterrestrial life. If oceans do exist beneath K218b's atmosphere, they may be shielded from harmful radiation, allowing microbial life to evolve undisturbed. The data gathered by JWST represents not just a technical triumph but a philosophical turning point. We're no longer limited to detecting exoplanets. We're beginning to analyze their atmospheres, climates, and chemistry with unprecedented accuracy. It's like peeking through a cosmic keyhole into other worlds, many of which may be more diverse than we ever imagined. The instruments aboard JWST are capable of capturing infrared light from incredibly distant and faint objects. This gives scientists the ability to look further back in time, billions of years, essentially watching the universe in its infancy. And what it has seen is astonishing. JWST's infrared eyes have revealed galaxies from just a few 100 million years after the Big Bang. These are the earliest structures in the cosmos, forming when the universe was still in its turbulent youth. What's startling is that some of these galaxies appear far more massive and developed than they should be, according to current cosmological models. It's as though entire cities appeared in a wilderness that was supposed to still be forming villages. This discrepancy has led scientists to question some long-held assumptions about how galaxies form and evolve. Equally captivating is JWST's ability to peer into stellar nurseries, clouds of gas and dust where stars and planets are born. One such region is the famous Pillars of Creation in the Eagle Nebula. JWST's view of the pillars, in infrared, strips away the dense dust and reveals stars in various stages of formation. It's like witnessing a divine forge in action, with each speck of light a potential new sun, each sun possibly hosting its own solar system. But perhaps the most emotionally profound moment in JWST's early mission was the release of its first deep field image, a cosmic tapestry showcasing thousands of galaxies in a single frame, some warped by gravitational lensing, others bursting with new stars. It was a portrait of the universe at its grandest, a reminder of both its scale and its intricacy. That single image revealed more galaxies than grains of sand on a beach and made humanity feel both infinitesimally small and immeasurably connected to the cosmos. Beyond deep space observation, JWST is also revolutionizing our understanding of the planets within our own solar system. When it turned its gaze to Jupiter, the telescope revealed auroras, storm systems, and faint rings in exquisite detail. Jupiter, already a subject of countless studies, suddenly appeared anew, more dynamic and mysterious than we had realized. Similar scrutiny is being applied to Saturn, Uranus, and Neptune, with early data suggesting new insights into their atmospheres and internal structures. Then there's Pluto. Though reclassified as a dwarf planet, Pluto has never failed to capture the public imagination. When JWST examined it, scientists were surprised to see evidence of complex seasonal changes, potential subsurface oceans, and surface activity that hinted at a surprisingly dynamic environment. Far from being a frozen, lifeless world, Pluto is emerging as a place of continuing geological activity, possibly driven by internal heat or exotic chemical interactions. The James Webb Space Telescope is also uniquely positioned to study comets and asteroids, particularly those that come from the distant Oort cloud or Kuiper belt. These icy bodies are time capsules from the early solar system and may hold the key to understanding how water and organic molecules arrived on Earth. JWST has the sensitivity to detect the faint signatures of water vapor, carbon compounds, and other volatiles escaping from comets, even when they are still far from the Sun. Its ability to track faint objects has also led to the observation of rogue planets, planets that drift through space untethered to any star. These lonely wanderers could be more common than we think and may even possess internal heat sources strong enough to support life beneath icy shells. The concept challenges everything we thought we knew about the need for a parent star and opens up an entirely new category of habitable environments. The implications of JWST's discoveries ripple far beyond astronomy. Each revelation challenges our assumptions about the nature of planets, stars, galaxies, and life itself. As we accumulate more data, we are beginning to understand that the universe is not just stranger than we imagined, it's stranger than we can imagine. New categories of planets, unanticipated chemical processes, and the sheer diversity of cosmic structures are forcing scientists to rethink how planets form, how life might begin, and even how the universe itself has evolved. And we're still just getting started. Every new observation is a puzzle piece in a much grander picture, one that's constantly shifting and growing more complex. The telescope's mission is planned to last at least a decade, with enough fuel and operational stability to potentially observe well into the 2040s. With each passing year, the data will become richer, more detailed, and more astonishing. One cannot help but marvel at the timing of JWST's discoveries. At a moment in history when humanity faces countless challenges here on Earth, this instrument offers a shared glimpse into something greater. It reminds us that we are not confined to this small planet. We are explorers by nature, reaching out across space and time in search of knowledge, wonder, and connection. As we wait for more findings from K218b and countless other worlds, we are left with the exhilarating realization that Earth may not be unique, and life may not be rare. The silent question that the stars have asked for millennia may finally be answered, not in words, but in light, captured and decoded by the greatest telescope ever built. At Discovery at 2.0, we will continue to bring you the latest findings as this cosmic story unfolds. Because out there, among the stars, the next great discovery is always waiting.